Hey guys, what's going on? So today we're going to be going over the Ricci scalar. You might see a little bit of a different setup now. I got pretty cool apparatus for Christmas that is helping me make better quality videos, better lighting as well. So let's get straight into the content. Again, make sure to hit that like and subscribe button if you're into this kind of content. Make sure to go onto my Patreon page as well, where you will be able to see exclusive content coming up shortly. Anyways, so let's get into the Ricci scalar. So the Ricci scalar is going to be a contraction of the Ricci tensor that we've talked about. So we're going to find that the Ricci scalar is going to tell us something about how areas deviate from flatness, specifically the ratio of the area of curvature to the area of flatness. But we'll see how all this works. And what we'll end up with is a summary here. So the summary here is that the Ricci tensor, as we recall, gave us something regarding volume changes. And the Ricci scalar gave us something, is going to give us something that represents an area deficit. Okay. So let's start computing the Ricci scalar. And another name for this is Ricci curvature, right? So, or not Ricci curvature, the scalar curvature, right? So this is scalar curvature is another name for the Ricci scalar. Anyways, let's get into this. So we're going to start off by considering the area of a sphere. So here is our sphere, but we really just want to compute this area here. Right, this area here. This is not exactly a semicircle, right? Because we're not necessarily going through the equator. Right? This here isn't necessarily the equator. But the way we're going to do this is we're going to integrate over the area. The area is 2 pi rho, where rho here is the diameter at this point, where this circumference of this circle. Okay. ds is going to be the thickness of the circle. Rho is going to be, again, that radius, which is, we can, through trigonometry, we can find is, rho is going to be this times the change in our angle, right? So these are the two relationships we want to keep in mind. And with that, we plug everything into here. Okay, and then from when we plug everything into there, then we can do some algebraic manipulation. We get this. Integrating sine, we get this from 0 to phi, or to theta. So from 0 to theta, we get this. Okay, so this is the general formula for calculating that area, right? So we can actually, I want to actually go ahead and circle this. This is going to come up in our visual differential geometry playlist as well. It's called Visual Differential Geometry and Forms, which is what we're working on as well every Monday, with the exception of last Monday because it was Christmas. But anyways, this is a general formula for finding the area of the sphere, or not the sphere, right? This area right here that we've put in green. All right, so the area is a function of little r, right? So if we call rho little r, then our angle, right? So just coming back up here really quick, our angle is going to be r divided by big R. Right, so r divided by big R, and so we get this formula right here. And what we can do now is we could say, well, we can compare this area. This is the area in curvature, with the sphere. What we can do now is we could say, well, what's the area on a flat circle? Well, the area on a flat circle is going to be this. Okay. And so what we get is this guy right here, or this. We get this ratio right here. And when we get the ratio, we can cancel. So we can cancel the pi's. We get this as a constant, right? 2r squared, little r squared, and then 1 minus cosine. We can approximate cosine with the Taylor series, like this. And then when we do that, we then get the this formula right here. The 1 and the 1 are going to cancel, and we get this minus sign distributes, right? So this is going to be positive, this is going to be negative. And so we get this. Okay. And so once we get that, then we come up here, and this is the formula we have, right? So the formula we have now is 1 minus 1 over 4 factorial times 2 over r squared times little r squared. And then everything else is going to be a higher order with respect to r. And so those are going to be negligible, right? Because if this, we're calling this r, if little r, if it's small, right? So if little r is small, then this is going to be, this is going to get more and more negligible. And so that's why. So we're going to essentially ignore this. We're going to say that this ratio is approximately equal to this. Okay. Now we're going to deviate a little bit, and we're going to say, we're going to talk about the Ricci scalar for a sphere. So the way we define Ricci scalar is to contract the Ricci tensor with the metric, or the metric tensor. And so this is what that looks like. This is an Einstein sum, right? So we can, this is what it looks like in full component form, in where n equals 2, right? So this is in 2 dimensions. And these are the off diagonals, right? So our metric looks like this, right? So E1, 1. These are our tensor. This is way too small. I'll rewrite this, right? Our metric tensor is E1 cross E1. What I'll do is I'll just select, copy, and paste, and then copy paste these guys. Right, so this was our metric, right? And then I'm just going to have to erase this one and this one, and then 2 and 2. Right, so just going back, rehashing on a few things. Our metric is the thing that mimics our inner product in our vector spaces on that manifold. If you recall, we had our manifold at every point in space. Then we had our vector space. We had an inner product, right? To mimic this inner product, we invented another space that did that, and that was the metric space, and the space of this is rank 0, 2 tensors, right? If it was like this, this is rank 0, 2 tensor space. And this is our metric tensor. So this is going all the way back, just as a rehash. That's what, so that we're contracting the Ricci tensor with this metric tensor. So there's another space here. There's another space here that has our Ricci. I'll do that in a different color. There's another space here that has our Ricci. I'll do that in a different color. There's another space here that has our Ricci. I'll do that in a different color. There's another space here that has our Ricci tensor with this metric tensor. So there's another space here that has our Ricci tensor with this metric tensor. So there's another space here that has our Ricci tensor with this metric tensor. So there's another space here that has our Ricci tensor with this metric tensor. So there's another space here that has our Ricci tensor with this metric tensor. So there's another space here that has our Ricci tensor with this metric tensor. So there's another space here that has our Ricci tensor with this metric tensor. So there's another space here that has our Ricci tensor with this metric tensor. So there's another space here that has our Ricci tensor with this metric tensor. So there's another space here that has our Ricci tensor with this metric tensor. So there's another space here that has our Ricci tens there's another space here that has our Ricci tensor, right? So, and when we couple, we're taking these two guys, and we're using them to contract into the Ricci scalar. Right, so this is sort of a pictorial image of the manifold and how we can organize our thoughts in that way. And this is sort of what it looks like all fleshed out in the Einstein sum. And you recall these two guys off diagonals, those are 0 in the metric tensor. If we're talking specifically about a sphere, we get this. And so for our sphere, we haven't really gone over this yet, but the G11 looks like this, and G22 looks like this. R11 is 1 and R22 is sine squared. We haven't really talked about specific examples yet. I'm telling you right now that this is what they are, and we'll go over specific examples in later videos. But just as a hint here, we have two matrices essentially going on here. One is our metric tensor, right? So our metric tensor, we have 1 over r squared, and then 1 over r squared sine squared theta. That's our metric ij, and then 0, 0, and then r ij is going to be 1 sine squared. And that's where these numbers are coming from. So these numbers here are really just this is this guy, these are this guy, this is here, and this is this guy. And what this all reduces to is 2 over r squared, right? Because this is just 1 over r squared. Sine squares canceled. So 1 over r squared plus 1 over r squared is 2 over r squared. And this is what our Ricci scalar is, right? So our Ricci scalar was this, and this all equaled this guy down here. So our Ricci scalar then is 2 over big R squared, where big R again was the radius of our sphere. So if we go up here really quick, we have our 2 over R squared. And so we can say that the ratio of the area of the sphere to area of the flat space of this particular region looks like this, where R again is that radius in flat space. So what is this telling us? This is telling us that the Ricci scalar tells us something about this area deficit, right? So if this is 1, if this somehow is really small, right? If this is small, this is going to be small. That means the area of the sphere to area flat, well, that's just going to be 1. So then that means that there's going to be no difference between the area of that region compared to the area compared to the area if it was just a flat circle, right? So the Ricci scalar tells us something about that. If R is small, right? We can imagine this, right? So if R is really small, then we're not going to get such a huge region to encompass, right? This is going to be quite small. However, if R was really big, right? So if the radius here is really big, then that's going to be a different story. The area per unit theta is going to be really big, and we're going to have much larger area to encompass. So in summary here, the Ricci scalar tells us how an area deviates from flat areas. So in the case of flatness, the Ricci scalar is going to be 0. If the Ricci scalar is greater than 0, then we're going to have positive curvature. Or not curvature, right? But this is what we want to picture in our minds. And if it's negative, it's in the opposite direction. All right. So we've gone over a lot. This is the point at which most general relativity, most tensor calculus stops. If you're taking a course in this, say in university or even on YouTube, a lot of places will stop at the Ricci scalar. And then they either might go into examples, a few examples, or that's just the end of it. I actually want to go a little bit further here. I actually want to take everything we've learned up until this point and go further. I want to try to go further into more advanced areas. So what I'm going to do is we are going to go over a quick review over everything. And then we're going to start introducing ourselves to more advanced stuff like the Weil tensor, Landcoast tensor, Plabonsky tensor, and all that kind of stuff. And other areas that don't really look at tensors themselves, but more geodesic deviation and stuff like that. And we're going to start bleeding into areas within general relativity. Let's go over a quick review really quick though. The metric tensor, we've gone over this. We've gone over the affine connection. All right. We found that we were looking at the connections between the metric tensor and the affine connection. That was the intrinsic definition of this connection. We then moved on to talk about the covariant derivative. We spent quite a few videos on that, and we spent quite a few videos on the Lie derivative as well. Right, so this was pretty early on. We covered all this. Then from the Lie derivative, we talked about the torsion tensor and how the Lie derivative played a role in the torsion tensor. And so we have the two equations here. The torsion tensor can be thought of as taking in two arguments, right? These are two directions, and spitting out a number, or spitting out a vector, right? Then the vector told us the distance, the vector, if we were to travel, say, in this direction, right? If we were to travel, say, in this direction and in this direction, as opposed to this direction and this direction, the Lie derivative is the separation vector that we talked about. The covariant derivative, or the torsion, the torsion tensor told us something about this separation, right? The curvature tensor tells us something about what happens to a vector itself as we travel in these directions, right? So the torsion tensor tells us something about traveling in these directions. The curvature tensor takes a vector z, right, and it compares it as the vector travels along a closed loop. And so we can calculate the components in these two ways as well. All right. And then we went over the torsion-free property. We went over metric compatibility as well. And so everything we've been dealing with has been torsion-free metric compatible. Then we talked about Ricci tensor, how to calculate the Ricci tensor. Ricci tensor was a contraction of the Riemann curvature tensor. And then we talked about scalar curvature. This is the Ricci scalar. And that was a contraction of the metric with the Ricci tensor. And what we found there was that the Ricci tensor gave us volume changes, and the scalar curvature gave us area comparisons. Right, so we're at a point now where we're going to get into more advanced stuff. And the kind of advanced stuff I want to start off with is talking about the Weil tensor. So the Weil tensor is going to be, I'll move this up a little bit. The Weil tensor and the Schouten tensor are the first two I want to go over. So Weil and the Schouten tensor are the first ones I want to go over. We're going to spend some time on these two tensors. The story here is that we are going to start off with the Ricci curvature tensor. we talked about the Ricci curvature tensor. We talked about the Ricci tensor. Sorry, not Ricci. This is Riemann. This is Ricci. This is Ricci as well. Ricci gets more real estate, if you will, when we're talking about this kind of stuff. But we stopped here. Right? We stopped at this guy. We're going to talk now about, or in the next video, we're going to talk about the Weil tensor. So we're going to spend quite a few videos on this probably because it's super important. It tells us something about conformal invariance. It tells us something about also the tracelessness of the Riemann tensor. And we're going to talk about the Polanski tensor also. Not the Polanski, right? This is the Schouten tensor. You get this mixed up because if you look up on Wikipedia, the Schouten tensor is denoted as P. And sometimes I think of the Polanski tensor when I see P. But anyway, this is how we're going to start, right? So Ricci curvature tensor is going to be some tensor, which is going to be the Weil tensor, plus another type of tensor, and we're going to say this spike here, or this not spike, this notation here is going to be something we're going to talk about as well. This something called the Kulkarni-Numitsu product. Kulkarni-Numitsu product. We want to understand that because what you'll find if Wikipedia is an excellent source on this, but not excellent, but it's a source, is that we're going to have to go over this product to make this, to make a rank 02 tensor a rank 04 tensor, so that we can add these two things to get this guy. But that's all to come in our next few videos. I hope you guys had a good Christmas. I have some big projects coming up pretty soon that are going to be starting on the 1st of January. We also before I go, I also am going to cover the Lenskos tensor, right? So that's mu, nu, alpha, beta. Actually, no. The Lenskos tensor it's actually denoted with an H, mu, nu, say gamma. And this is related to the Weil tensor. When we go this, so this is the Lenskos, C. No, I'm spelling that wrong. Lanzcos. This is going to get into more physics, right? We want to go back. We're going to want to go back. We're going to want to talk about the electromagnetic potential, the analog to that when we talk about the gravitational potential, and that's going to be the topic of this guy. This guy's probably going to come later, just because in my opinion, it's a little bit more difficult to understand than these two guys. But that's what's to come. And I hope you guys have a great rest of your day. So again, make sure to hit that like and subscribe button. Make sure to go into my Patreon page as well. And I'll see you guys in the next one. Bye.